Hello and welcome. What are we doing now? That's right, we just installed the GPU. And I turned off the computer and ate dinner. So, it should be off. Otherwise that dinner cost me an extra $1 or $2. And it's off. So, start the machine. And what we were going to be getting back to now is this CNN Model 1 notebook, where we were training a basic convolutional neural network. Then it was going to take 5+ hours per epoch. So we added a GPU, and now it's going to go a little bit faster. So let's see if our computer's turned on. Also a little tempted to scale this up so that way it hides that top bar of the monitor. I wonder how much nicer that would look. How freaking cluttered it looks. I do it this way. Let's see if we can scale that up. That's the image. Screen capture is what we're looking for. Scale that up there just a little bit. It's always going to chop off the right side of the screen. That should be okay though. Nothing too important over there. There. So now, if we jump here, and we jump over here, should be alright. You would think I'd have 2 monitors here and I'd be able to see both, but there's only 1 monitor. Alright. Screen. Jupiter. Copy the IP. And here we are. Notebooks, untitled folder, CNN Model 1. And the first thing let's do is TF check if GPU is available. tf.test.is GPU available. Let's see if that works. Let's see if we can figure out if our spectrogram is attached or if our GPU is attached to our box. TF test GPU available. They got mad at us. Oh. No. We hadn't mounted our data directory, so it couldn't find any TFRecords, and it was upset. Now it's happier. tf.test.is GPU I actually have to evaluate this. True. Fantastic. Well, let's test it this way. Is it going to take 5 hours anymore? Or is it going to take like, what, 10 minutes? 10 minutes per epoch? It's loading everything up. I really need to change it to where there are more workers. Like you can change multiprocessing and workers to where it gets all your data ready and cached and going. We'll do that in a few minutes maybe. Because it's one thing, right, to get the GPU attached to it and running. It's another thing to make sure that you're using it properly. Check that out. A minute. Maybe that was 6 minutes before, not 6 hours. Either way, you know, it's 1/6 the time. All right. So we're gonna let this run and see where we get to. Right now we're at what, like 1.9% accurate. But our loss is decreasing. Accuracy is increasing. So we're getting somewhere. So how about we spend, like, let's say $3. Let's check out how much this V100 GPU is. the V100 on an hourly basis. Oh, $2.48. I thought it was $1.48. Which one's $1.48? It's the P100. I can run that. And the K80, which is out, is 45 cents. Well, anyway, that's running. And we're still decreasing. We're at 3%. So you'd wonder, like, all right, so what number should I put in for steps per epoch? And really just kind of depends on where we want these checkpoints to be as we're looking at our rates and how they've been improving, right? Because we're running this for 10. So let's say it runs for 10, and we want to make sure that our accuracy is increasing each time. So we want there to be enough steps per epoch that it would have increased the accuracy. Like if, let's say we had 10 steps per epoch and we were doing 10 epochs, accuracy wouldn't increase. Yeah, and if you did too many, then you're just going to sit there and wait and not really get any time to look at a fresh view of it like this and be like, all right, where are we at? We're 13% accurate. That's decent. It'd be nice to see what this actually comes up with after we have trained a model and go back through and predict the audio. Which, while this is running, like let's say we let this run for the next 10-15 minutes. And while this is running, we go ahead and create that notebook. We will create a notebook to cycle through all of our audio files and use this model to predict them. For continuity's sake, or discontinuity's sake. Hello and welcome back. So today, on a full screen, we're going to be going back to that notebook that we were just talking about. And we're going to see if we can predict our audio files. So let's say we select and download audio spectrograms. I think I put it all in spectrograms. Let's see what's going on here. Yep, so we have all of our settings here, and we've gone over this before in a previous video. We're pretty much going to be going through all of our birds, getting all the audio files for them, processing that audio file, turning it into spectrograms. And then before we were writing TFRecords, we're going to skip that step this time. We're just going to go ahead and predict it. Something we should think about first, though, right, is we can't parallelize this process. Whenever TensorFlow is running, it's going to use up all of the cores. And you can't have 10 versions of it running at the same time, trying to use up all of the cores at once. So really, though, it's no big deal. We can just cycle through one at a time and do all of these in series. It's just a thought before, because right before we have multiprocessing and we have this pool going on and we can do all that. We can't do that this time. Cannot do that this time. Create spectrogram, download and wave. Same exact functions as before. We're just downloading a file from Google Cloud. Here we're creating a spectrogram from some audio data. We're using this transform from the Nayuki library. It's a fast Fourier transform going over slices, NFFT or half NFFT lengths, which we were set to 1024. Blah, 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 blah. Anyway, we're downloading an audio file. We're creating a spectrogram from that audio file. Here, let's see, we created these spectrograms here before. We're going to go ahead and tell you what, let's make a copy of this notebook. I already changed some things, didn't I? There. Save that, make a copy. We're going to rename this copy. What are we going to rename it to? We're going to rename it to classifier. We're going to call it 105. Because in this time right now, we have 105 birds. All right. Now we're going to get rid of the pool. We probably already have the audio file, but just in case we don't, we will let it. We'll keep the Google Cloud storage in there so that way I can download those things. Boom. We got clouds, got Florida birds, spectrograms. Now we can go here. We're not going to be removing any files. Get bird. What does get bird do? Okay. So what this is doing is it's going through a bird and getting all of the audio files up through max files for that. What are we opening up here? We're opening up the spectrogram for it, really. Oh, because we're writing it. Creating the spectrogram here. And what is this? Spectrogram. Because we're grabbing slices of it here. Right, because we're going for window index, start index, and enumerate range from 0 all the way through the end of the spectrogram minus 1 width, going by skip. So in other words, we're starting at 0, we're reading 1 width in, we're skipping by some amount. I think it's like 100 here, maybe it's 512. What's our skip set at? 256. So we're pretty much skipping half of a window and then doing it again. And grabbing a slice of the spectrogram right here. Spectrogram is this slice, all of the height, and then for the width, going from our start index over to start index plus width. Boom. So at this point is when we would want to classify this file and see what it is. And toss this into our model. So our model, whenever we're predicting or classifying things, it's gonna expect data in the same shape in which the training data was, right? So you had a batch of things. Whenever you're training, whenever you're classifying, you're also gonna have a batch of things. You could train one item and it'd be a batch size of 1, but in this case, it will be a 4-dimensional item going in, right? The first dimension being 1, because there's one item, and in this case, 512 by 512 by 1. Yeah, because we are shaping it back out with that one number at the end. Okay, so what was the point in that? The point in that is how many items we want to classify at one time. Could we take an entire file and classify that whole file at once? And I think that we can safely do that because we have this max secs in there. So there's a max amount of seconds that we're grabbing from one file. So this never will get ridiculous. So what if we just do something like this? Spectros is this list. Yeah. And we'll just say spectros dot append spectro, and then here predict. I think it's predict spectros. And then one thing that we have to consider for this, right, is do we take the average? Do we take the max? Do we take the sum? I mean, considering everything could have 90 seconds and you could just kind of like pad it for the ones that aren't 90 seconds. How are we actually going to classify a file? For example, let's say we're taking 90 seconds of data, and at second 30, there is a pristine call for a bird, but there's only one call in there for the entire audio file. And it's right? Like it's the bird that is the same as the label for the audio file, and it's great audio, but it's nowhere else in the file. Everything else in the file is just like background noise. So if we took the max, right, that file would have a really good score. But if we take the average, so if we have, let's say, 10 windows in this file that we're classifying, and so all the other ones, they wouldn't have a high score. This would have a high score. Averaging out, the file overall would have a low score. Or do we want a file that has, like, is that a good file is what I'm asking. I don't know. So let's write the code for both, and we'll just see what happens. Really, I just want to get to where we can listen to these audio files and see what they sound like. So get bird, these are all going to be our... We're going to create this variable right here called asset ID scores. going to be a dictionary. So here we're looping through all of our asset IDs. Oops. This is the end of the loop for this one. So we're going to say asset ID equals this is what it would be if we were taking the max. And then if we were taking the average, maybe something like this. Dimension might be wrong on some of this math right here, like I might have to go back and change it, but we'll find out. Okay. So after that bird, let's see, yep, right there. Return asset ID scores again. All right, bird items, because I was using a pool here. We're going to skip that pool. We got to pull in this model. So let's see how our model training is going. It should still be going. Maybe not this file, not that file, not that one, not that one. There we go. So we're on our 8th epoch. Ooh, look at that. We've gotten to 49% accurate. Our loss, it's still decreasing. It looks like we started back up there though. And 133 seconds each. It's about 2 minutes. I'm kind of curious where we would have actually ran without a video card. I don't know. So we'll let it go ahead and finish all 10 of these. And then after that, we'll hit model.save. And we're just going to call this Florida birds.h5. I think h5 is the thing. So here we already have TensorFlow, Keras models, .load model, Florida, did I call birds? I meant to call it birds. Florida birds h5, cool. Florida birds.h5. Does that make sense? Training the model there, we're saving it, we're pulling it in here, and that's where we're going to grab this classifications from. For now, we're going to do the max. Does that make sense? That definitely doesn't make sense. We're going to have to clean that up some. Because classifications is going to be coming out as what? I think it comes out as, let's look at our model. Is it like a softmax array of our number of classes? Yeah. So we're looking at 105 coming back out. And so if we have a list of item, right, and each one has 105, 105, 105. And what we really want as our score here is the max of classifications across axis 1. Yeah. I think. Okay, training done yet? On delay. Got, what? 4 minutes left. Let's see what else we could add to this in 4 minutes. So we got to get this bird. We're going through and predict everything with it. And then what are we going to want to see? We're going to want to see... This is expecting him as this weird format too, right? Bird index and item. Because directory, spectrograms, what is this? Let's take out some of this other code. Don't think I need that in there. What does it need the bird index for? Audio files, item audio, because the audio is already coming in. right? Coming in as this item with the bird index and the item. Do we use bird index anywhere else is what I'm wondering. We use it for this directory here. Hey, okay, straight on. Import I found out display team. Audio. So this, and then I can clear OBS to hopefully play this audio over it. So this is our audio file of bad index, right, one that predicts well. And our list here is right? So models tracking for so with two accurate predictions, an inaccurate and inaccurate. Inaccurate for a while. Listen to the audio. All right. Is it cardinal? It's got to be something glaringly obvious that I'm missing there, but we'll get back to it. So this bird, and somebody talking for let's see, head of the index and the bird. The bird's coming from there. So bird time exact kernels. Check this out. Bird index is equal to 0. As our model bird item. Pretty cool. It's another one. Cool. So try and see what the score is. Index. Border 5 assets. Classifications. Border birds. Spectral is fine. Scores. Bird. No, not scores. Okay. Index. Adding function. Right. Yeah. Cool. The whole purpose of all this is just to find which audio files in the training data actually fit the model fit training data. Under the assumption that, for example, here it's not cardinal. We're doing the training cardinal. Parts of the audio file that aren't cardinal that also is in the audio files. Cool. People talking. Bird. Then. Yeah, we won't match instead. Easy way to filter down all for audio. Let's listen to this one real quick. This is one of the ones bird. I understand three, so this should not be a cardinal sound. So we've created this little tuple here that has the index of the class coming in, and then some other data for it there. So and we're sending it in here. We'll grab that back out. The index and the item. The bird is equal, that's interesting, to the item key of the bird. Then we're just printing that back out so that way we can see it. Again, before we were running this as a parallel process, so that way I really wanted to track what all was going on. Cool. So this is exactly what we wanted to get to now. So we can train model. Still want to check what's going on, but it should look a little bit more sane. And we can filter training data down to actual good data. For example, we can filter these down to, so we got that. They're only got this. The right class. Now, look through everything, check if it meets the right criteria. If it does, create spectrograms, save it, and go through there and actually have the model in that filtering process. Or even better, probably go and pre-print it all, save it some file, and then go through the training process. Because if 20 seconds out during your development, then if you go through, accuracy is still around 50%. Next step here is call that towards the end. Could we improve this model, right? So we're at 50% accurate. We can make that better. Probably. That's the question about the attention mechanism. Too bad. So maybe we need that next. Yeah. Maybe we'll take a little bit of attention next. Until then, thank you for watching. It's been fun. A nice 5 minutes with how long we're really interesting. And here's the audio. We can play bird sounds all day long. Cool. I look forward to it. That win. And the ones that don't. Okay. So we're going to say that we called this. And I can go over here and do model load. No, we are unhappy with that. Why are we unhappy? All the way down to computer runtime. Oh, because we already have a notebook running. And it is not happy to do another one. Kernel shut down. Yep, shut down that kernel. Come back over here, and we're just gonna restart. You just saw what happened, right? Like we already have a Python instance open that is reading that GPU, and it already has it full of other stuff for training. And when we try to give it more things from this GPU, it got mad. But now, let's see. We loaded up our model and check this out. We can do model, summary, and see the same stuff we had in there before. They're same 48K, 49K training variables. Okay, there's that, there's this. So, yeah, 0 is the northern cardinal. We knew that because it has the most. So our classifications coming out are this. Does that make sense? What else? What is still running now? Classification with that, print classifications. 1, 2. Oh, because we're going through each scores for each one. And I went through them fairly quick. Oh, because we got angry. Export X must be a non-empty array or data set. Scores get bird classifications equal that. Okay. So we're mad that Spectros is a little light. if the length of spectros is less than 1. Continue. And also, let's go ahead and just, for the sake of this, do one audio file. Okay, so there's our score coming back out. We have this asset ID here. And what? We have an array of 0.19. Does that make any sense? So what else do we want to know going in? I would like to actually know the length of spectros going in. How many are we classifying? The length of the spectros. Okay. So, because it looks like we're just sending in 1 here. Let's make sure that's the case. 1 spectro. Okay. And we are looking for the max across axis 1. So we're going to expect that a 0.19 exists in here. Or a 1.9. Do you see it anywhere in here? There it is. Boom. Because I call it MP max. I want MP arg max, don't I? That's going to tell us that it is some out there number. 93. Kaplooey. Is that good? Let's try another file. Let's see what happens. This one's going to have a few more. There we go. 13 spectrograms. 0, 0, 0, 31, 10. See, look at that. That's what we want to see there. So let's listen to that file. What's the best way for me to listen to that file? Pull it up over here. I think the best way is going to be to pull it up over here. We'll be back.